Alright, hey guys. Today we're doing CodeJam round. That's the thing I forgot to close. Doing CodeJam round 1A, and yeah, it seems like I'm always consistently a bit late for these, so let's get started. So I had a bit of a cough lately. Hope that's not too detrimental. We have a list. We want them to be strictly increasing order, but we cannot reorder them. Our only option is to change them by appending digits to their right. What is the minimum number of append operations? Okay. So I suppose we append to the first value to make it, let's see, appending can only make it larger, so appending to their end, right? Yeah, to the right. So appending can only make it larger, so we want to start here. Then we want to append like the minimum number of digits to make it, we want to make it as small as possible, but still larger than this. So strictly increasing. So if the numbers are equal, we have to append a 0. Let's see. The numbers shouldn't get that large just because, like, numbers shouldn't get that large because we can sort of control how large they get. Like, if we make them all within the range, like 10 to the 11th or something, then we have basically 7. Actually, no, wait. No, they could be large, couldn't they? Yeah, they could. Actually, that is a problem. Never mind. Disregard what I said. So it's really a string problem. Let's see. So we want to find the smallest number such that this is larger. Yeah, alright, so it's really a string problem. C into SSI. So for I equals 1, as then n I plus plus. And it's equal to 0. Wait, how does it? Okay. Okay, so basically, if they're equal, we need to so let's see, if SSI is greater than or the string comparison itself is good, continue, because we don't need to do anything. If SSI is equal to SSI minus 1, if they're equal, we put a 0 onto this, and let's see, what do we do next? If might take a cough drop at some point. Right, so what do we get afterwards? Otherwise, let's see. Actually, so we know SSI is less than or equal to this, so really we can compare their lengths. If their lengths are the same, then we have to append to this, and therefore we append to 0. Otherwise, we assume SSI is shorter. So now, actually this I have to be careful about. I have to ensure they're equal length here. Alright, so if it's greater length, we're automatically done. If they're the same length, then they're, and this the second one is greater than the first, strictly greater, we're done. Otherwise, it's less than or equal to, we have the same length, we have to put on a 0, then we continue, because that's enough. Otherwise, we have a smaller length. So we figure out what we need to do. We compare it to the prefix. Oh, this is, oh, Jesus. We compare it to the prefix, and we get some casework, I guess. Wait, how does, hang on. If C++ does string comparison lexicographically, let's see. I'm just gonna do some tests. What do I need to test? A, well, that one's obvious. Also, we're reading in multitest, so I'll just do 1. Okay, should be true, yeah. Okay. Good, so it compares, actually wait, what I did want to test is B and then some like AC, which should be true, 1A. Yeah, okay. So if SSI is less than, no, if SSI is greater than SSI minus 1, we know that we have to, basically, we have to make it so, actually automatically the prefix is going to be larger, so we can just stick on zeros. So while SSI.length is less than SSI minus 1.length, then we do that, stick on zeros. If we're already less, then we have to be strictly greater length. What? So then continue. If we're strictly less, we have to be strictly greater length because we're already like worse off. So plus 1. Otherwise, they're equal. So we look for the first thing that isn't a 9. We're trying to increment by 1. So like 4 LOJ equals SSI minus 1.length. J. Basically now we have these two strings. We know they're equal. And we want to make it so this blue part is strictly greater than this part. So if this is all 9s, then we can't do anything. Otherwise, we're trying to make it as small as possible. So we find the first location that, actually no. If they're all 9s, then we can't do anything. Otherwise, so we're kind of just incrementing the number. Okay, that's cool. let's see. So bool all 9 is equal to 1. So if SSJ is not equal to 9, j minus 1. If the previous string is not all 9s after this, then all 9 equals 0, break. So if not all 9, ants plus equals, now we can make them the same length. SSI dot length minus SSI dot length. We make them the same, except now we have to increment SSI by 1. SSI minus 1. And now the same thing. Then plus SSJ minus 1. Wait a second, something's messed up here. So if this is I minus 1 j, the previous string's value at this position is that I minus 1 j is not equal to 9. Should be I, should be I. This will go till 0. Okay, very much don't trust this. So if it's greater length or it's the same length and we're greater, then we're automatically done. If they have equal length, we put a single 0 on because we can't do anything else. If this is greater, we put down zeros until we can't anymore. If it's less, then we have to make it like larger length. So we put down zeros again until it's strictly greater length. For this, it's simply SSI minus 1 dot length minus 1. Say n equals 3. Yeah. So see, all this is using I, so that's fine. We check for all that. So we go from the previous to this one. If we find a single thing that isn't a 9, then it's not all 9. Alright, so if it's not all 9s, then we can make SSI equal to SSI minus 1, then increment it. So if it's a 9, it carries over to a 0. Otherwise, we get the carry ij. Yeah. Else. Otherwise, we can't really do anything, so we have to make it the same length again. So it's really just this logic. Alright, so we look for the first non-9, then we increment that, then we're done. Okay. Sounds reasonable. Whoa, what was that? I need to download it. Cancel. 4120. So make it 100, 700, 1000, 10, 1000, 4, 19, 100. 1, 2, 3. Yep. 1. So let's see. What are the cases? So we have like a lot of things to test. Let's just test everything. 7. So 1. Let's see. 9, 10, 11, 12. Oh wait. 7. 2, 9, 10, 2, 11, 12. We test equal length. So 13, 13, 2, 13, 12. 2, 5, 400. 2, 4, 4, 1. The length is a problem actually. This is sort of a pain. because it'll determine this is less no matter what. Should pass this test. Oh wait, what am I doing? Something's messed up. This should be larger length. So this should be like 499 and 5. It should be like 401 and 4, and this should be 404. And it's going to be a bit wrong, but that's fine. So yeah, 0, 0, should be 1. Should get 13,130, 13,120, 499, 500, 401. Okay, yeah, something's messed up here. Because it always thinks that. Okay, let's just like bool less is equal to 0. If SSI j is less than SSI minus 1j, else if it's greater, break, otherwise if it's equal, continue. If less, (401, 402, 400, 401). Perfect. And now for the final case, 499, 4. Yep, that is necessary. Actually, one more. 4194 should be 420 and 2 operations. Cool. All right, seems good. I will test that out. This is local, by the way, so it's not going to print that when I actually submit. Okay, let's read the next one while we're waiting. You're playing a new solitaire game. You're given a deck of cards, and each card has a prime number on it. Okay. Multiple cards may have the same number. Got it? Cool. Not the fastest, but yeah, we exist. So just playing safe here. Although there actually weren't any hidden tests, so this wasn't that bad, but whatever. Doesn't matter that much. Just going for top 1500. That's basically what the goal is. Select group of cards, sum and product. 2 groups. The sum of the numbers in the first group is equal to the product of the numbers in the second group. It has to be primes. What's n? That's a lot. Okay. So really, like, we don't have that many products. Like it's 15 over log 2. So we can have at most 52s inside. Because like the sum is 5 times 10 to the 17th. So like when we have small numbers, I mean, like we don't take that many primes inside the product, which means everything else has to be part of the sum. let's see. So if we take the sum, we're going to subtract some of the things from the sum, and those will be added into the product. And to do it in such a way that the sum is going to be divisible. Or like the sum, yeah, the sum must always stay divisible. Or the final sum must be divisible, because like divisibility is equality to, what is the last symbol? Last symbol is 2 7s and somehow it becomes an 8. Sum of the numbers in the first. Card. What? Very confused on how this works. Oh, do we have 7 2s? Oh, I guess that's how that works. Okay, that makes considerably more sense. I don't know how we would get 8 otherwise. Yeah, okay, so I suppose we have like a lot of 2s, a lot of 3s, a lot of 4s, etc. What does that mean, to have a lot of a certain number? This thing looks like it's ticking down a lot faster than it actually is. There's still 2 hours left, but you can like feel it moving kind of. Maybe you can't because my screen's so laggy it'll be frozen the whole time. But who knows? So really, like, there aren't that many products. I don't know how much that helps us though. There are most 95 primes. But there can still be like a lot of things. Case 2, note the cards are the same. Yeah. The number of different sums we get has to be small, doesn't it? So if we're taking at most 50 of the primes and the primes are at most 500, then regardless of what the products are, the number of sums we get has to be small. Which is interesting. And what that must mean is that, like, yeah, so we're taking almost 50, or like whatever log of 10 to the 15 is, it's like 50. Taking almost 50 things, taking almost 50 primes, and in any case, that means that the sum is at most, what would it be? It'd be like 50 times 500, so 25,000 less, which means we have at most 25,000 sums to check. So really what I'm saying is we're assuming we put all cards in the left side, then we're going to move some of them over to the right side. Now, because the primes are greater than 2, we move at most 50 over, meaning that the sum we move over is at most 25,000. Meaning that if we just check all possible sums, we can prime factorize them and we'll be done. Cool. Okay, CN2 stuff. CN2M for So even though there may be many different possible ways to get those sums, it doesn't matter. So that's like a knapsack. Bool dp for how this works. So we're basically checking yeah, bool dp for some stuff. What is the stuff? It is some stuff. But like what kind of stuff? What am I doing? Come on. Get your head in the game. We still have 2 hours. So we're saying dp on a certain number of elements and a certain sum, which is most like let's see 30,000. There are 100 tests, won't take that long to reset. So memset dp0 size of dp. Right, now okay, for each value we can make 0 with 0 elements. It's very true. For j equals 0, j is less than 27. What's happening? Is that Alexa? Okay, anyway. I'm right on this, right? Like am I saying things that make sense? That we only take I don't know why I'm really like not in it today. I don't know what's happening. Maybe it's the 9 p.m. contest. Maybe it's the fact that I've not slept much recently. So could be any of those things. Let's see. Lim equals 0 for we'll just set it to 50, whatever. Min 51 and AI, no, BI for so dpij basically says, can we get this sum? So dpi plus 1, then this should be j plus, actually that's fine to have it be 0. Is it? Right. So dpi plus, just gonna do that. Yep. So if dpij for k equals 0, k is less than count, k plus plus, so we're going to take, it's going to be bi times k, ai, the prime, is equal to 1. Which is equivalent to saying it's equal to 1 actually, because we just checked that. So, not smart of me to do. Yeah, so actually something else I can do is just this. It doesn't matter. Alright, so now we're asking, can we get this sum? What am I doing? Let's see, so it's like 27,000. So if dpmt, if we can get this value as a sum of some of the values, then essentially what's going to happen is we're going to say for each something. For each something. What's something? What does that mean? If we can get here, then we're going to try this sum. So, and t is let's think of, this is a stupid check, but I've been doing stupid things, so can't hurt to check that. So then this is the required value. So now let's see. Oh, cur is equal to s. Actually, cur is equal to r. Yeah. What am I doing? Okay, so for each prime, for the number of times we can take it, bi j plus plus, if r mod ai is equal to 0, and yeah, else break. So basically just prime factoring it. If r is equal to, let's see. So if the current number, if the sum of the prime factors is t, and we did successfully prime factor it, and this is equal to s minus t, break. Then we print it. And note that it defaults to 0 otherwise. Dude, I've never felt this bad before. I don't know what's happening. Why is this not? Oh, I made these ints. Oh, that'd be a problem. I'm glad I caught that. Jesus. That was not something I knew had happened. 01708. Okay, let's see what's happening here, I guess. So when we tried 10, what happens? Why do we not get 10? What's with that? For I equals 0 is the non plus plus. So for j equals 0 stuff, if j plus ai times k is greater than, because again the sum is at most 25,000, so we're fine there. So in fact, this should test everything, and this doesn't really matter that much. So I guess we're good. Let's see. Actually, this DP doesn't really matter. Do I even need it? Do I even need it? I feel like it's just overcomplicating things. See if I just don't use it, what happens? It shouldn't affect anything, right? It's still like, in the worst case, it's always possible anyway. Yeah, I don't know why I'm doing this. Why did I do this entire thing? This was just stupid. Why would I do that? What am I doing? This was so simple. Like it just does everything, yeah. Let's see. So 2 to the 50th, 40th. Need that number. Come on. 2 to the 40th. Fine. Let's see, and that's good enough. So I'll have this. I need this plus 50. Well, actually, this plus 49, because we're going to move 49 of them out. 1, so 61, 2. The answer should be 2 to the 40th. Oh, need 1. What did I do wrong? This is 2 to the 49th. Oh, wait. 2 to the 48th. Why would I try Google again? Why am I doing these things? I don't know what I'm doing. Plus 49. That should work. Alright, because now we move 49 of them over, and then the rest of them become that. No? Does this make sense? So we have 2 to the 49th on one side. 98. Wait, this is the exact number. 2 to the 49th. Wait, 0? It's 0. Why would it be 0? Oh wait, the remainder is that. What am I messing up here? So this is... Oh, I'm an idiot. Using that as the prime. Okay. Alright, there we go. Looks good. If it passes the first two, it should reasonably pass the last one, because I just tested like the largest possible case. And again, the sums are going to be at most 50 times 499. Right? Yeah, because 2 to the 50th. And it's much less than that actually, but I don't really care. Finish pretty quickly too. I trust it. Hopefully it passes. Don't really want to fail system tests or something dumb like that. Is this a randomization one? It is not. It is randomization. Expected score. Here's an exam with Q true or false questions. The correct answer is either true or false. Each student taking the exam selects either true or false for each question, and the student scores the number of questions they answer correctly. And students have already taken them, you know the answers. Assuming that the... Okay. Seems good. Still very not fast, but... Why, I just won the round? Maybe. Actually, kind of depends. No, he just won the round. Wow, that's pretty good. Tourist submitted A and B. I guess that means he's playing safe or something. I don't know. Anyway. Being so slow tonight. I guess that's fine. Slow but steady. Reverse art from the qualification round. Nice. Wait, what am I... Yeah, okay. And students have already taken this exam. For each of those students, you know the answers they gave to each question and their final score. Assuming that any sequence of answers that is consistent has the same probability of being the correct sequence of answers. You want to maximize your own expected score. What? There are N students who have already taken the exam. For each of those students, you know the answers they gave to each question. The hell? Students know the answers they gave to each question and their final score. Oh, I see. Any sequence of answers that's consistent with their scores. What's n? N is 3. N is 3. N is at most 3. N could be 1. And 120. 2021. Okay. 120. So that means how many like possibilities are there? That's the first question. Not sure it can be that many. Those are some big numbers. Do we really need big numbers here? Those are some massive numbers. Yep, okay. Alright, we're gonna need some sort of stuff here. Yep. Significantly larger than 2 to the 64th. Use big nums, I guess. And copy someone's big num template. That's not a problem. What I really need to do is some other stuff, right? So we saw like dynamic programming or something. It's the number of solutions how does this work? It's like a 3D DP or something, so it's the number of can't be the maximum score, right? That's stupid. These samples are terrible, aren't they? Given the score for FFT is 3, the sequence of correct answers must be FFT. Given the score for FFT is 2. What are we supposed to do with this either? This is just useless. So it can be like 4D DP or something, which is stupid, but it's like the number of ways to actually wait, 2 to the 120th should fit in into 128. I guess that's fine. Hopefully they support that. It can't be the maximum. That cannot be the case. Is it guaranteed consistent? Yeah. Which is like 5D DP, that's not gonna pass. Basically, it's like the number of possibilities for that's certainly not gonna work. Can do better than 5 DDP, right? It's 120 to the 5th. There are a lot of tests, so we're gonna have to do better for sure. Maybe? I don't know. What can we get? We can get 2 to the 127 and 2 to the 60th. No, 120th times 100. That's so close. That's so close. That's so close. Actually, it should be times 120. Does that ruin it? It barely doesn't. Did they choose 120 specifically so that into 128 would work? Okay, anyway, we should like solve the problem before trying to figure out if we need big nums or not. So let's see. Again, one possible thing that can happen is like we do DP on the number of sequences let's see, we can always make n3 if we just like the students really just exist to give information. So we can really stick like 2 other students out that both have the same score for that. Yeah, it's like the number of sequences that have like A things in common with the first, B things in common with the second, and C things in common with the third. So it's that we've used a certain number of characters and our expected score is that. We cut something out? Expected score is something. Still recording, right? Sanity checks as always, just to be sure. Yeah, it's expected, I guess. So like any valid sequence will like work. It's like we're optimizing each character individually. Like of all possible sequences, yeah, for the first we can do bit mask, for the second I don't even know. But for all possible sequences, what we can do is we can like that's interesting. It is n cubed, isn't it? It's n cubed because like the states we visit are weird. Actually, I don't know how that works. So do some like forward and backwards DP. Like if we can solve for like every character but this one. We can say we need the number of things that have a certain number of oh, and actually something that's interesting, that there are really only like 2 to the n possible like types of tuples of answers. So we have a certain number of those. And each one will like what's each one do? Well, it makes the DP kind of easier, maybe? Does it? Does it? The number of valid sequences in total. First, the number of valid sequences in total. Then we're summing up over the number of like total correct answers we can get. I'm gonna just use a big num to be safe, but we're summing up over the possible correct answers we can get. And to figure out like a specific character, we need the number of sequences that use everything else and have that be false, for example. Or the number of sequences that use everything else and have that be true. And then to maximize it, we take whichever one has more, and that's how many we get. To maximize, we take whichever one has more. Is this something we can do in n cubed? Or n to the 4th, I guess? N to the 4th exists, but it's not the greatest. Right? So, like, and these samples are awful. Can we combine DPs? Yeah, I guess we can. So how does this work for time? It's not going to be so great in terms of time. How many possible inputs do we have? These are the things I'm considering now. Like, I don't trust the time here. How many solves are on this? Are people doing it better? A few. Oh, test 2 is hidden too. Interesting. So many people haven't really solved this after all. people failing on that. What was this one again? Oh, right. Just a bunch of casework. Well, maybe there's a more elegant thing, but that's what I know of it. So like this will pass test set 1, it'll pass test set 2, it might TLE on test set 3, that's the problem. How do we not TLE? Can theoretically pre-compute DP values or something? Suppose we do a ton of pre-computation, then what? If we do a ton of pre-computation, it's not that much to be done, is there? You really just need the number of sequences. It's still into the 4th. I really don't trust time here. There's so many tests, but are all of them going to be max tests? If they have 2021 max tests, there's no way this will ever pass. There's no chance in hell. If we do maybe like 2021 times 120 cubed, that might pass. But if we do that over 10 to the 9th, yeah, I mean, it's going to take multiple minutes. So I'm guessing they want it to be cubed. How do we make it cubed? Or we can pre-compute stuff. In either case, there's some stuff we have to do. Oh, they did this. Nice. That's good, because some people didn't notice the harder sample before. Alright, so I mean, wait, how many people are solving this now? Are people like full solving? Yeah, okay, this is a thing. Let's do better. What we need to do is also a problem with memory, isn't there? Memory was a gigabyte. It's not the best. And we're doing big nubs, aren't we? Like, this is not gonna be good. What do they want from us? Well, actually, there aren't gonna be that many sequences that fit it. Do we really need big nums? Actually, wait, no, it is at most 120 times 2 to the q, but it's like not even that bad. are we pre-computing? We're pre-computing for each like tuple of stuff that's happening. We're computing the number of ways to actually that shouldn't matter that much. Really don't think I get this. It's just gonna take too long. Interesting how this has a 2018 in it. Is that intentional? If I take this fraction, 65. So it's just barely better than this. Yeah. So again, somehow we have to restore the sequence. I'm not frozen, I'm just not doing anything. Just thinking. And the score for f of t is 3. Guess I can just spell things out. Do we need that much? So you can like break the things down to like, for example, on this question, the students answered this on it. Then like something. With that, like the number of possible sequences are not that many. I can read the input. Now we assume we're solving for 3. And that basically gives us some other stuff we can do. Don't know why I'm being so slow on this. But I am, so that's how it is. Yay. I don't know what I'm doing. That is a fact. So 120 cubed. Isn't like determined? If we know 2 of the expected scores, do we know the other one? I feel like we wouldn't, right? That wouldn't be the case. For each thing. What do we do with it? And if we store the expected value in the thing, what does that do for us? That can't be a state. stand up and pace around like I sometimes do. Maybe that'll help. I don't know. Get my brain like alive because it's not right now. Consider some set of values. Taking the values out of here, like 8 times 120 cubed is probably fine. Even that's a bit sketchy. 120 to the 4th is like too much. So we need to figure out, can we do the dp and cubed? I really don't know how we would. For each value, we have 8 distinct values, which is the thing. We have 8 distinct values. So what does it mean? What does it mean? What can we do? What can we do? I don't even know. What can we do? Number of students, number of questions, each of the x, and y. What can we do? Take one value here. We're gonna some stuff. One of the things that are gonna happen is sum down to be false, sum down to be true. I have another total number of possibilities. Another total number of possibilities. Another total number of possibilities. So how many of them are this and how many of them are that? Right? That's the idea. Do that as subset of dp. Suppose we set all values to false. We have to change some of them to make it true. Change some of them to make it consistent. Like suppose we set the sequence to what the first person answers. Now, what happens then is that qualify without this, so it doesn't make that much a difference, but solving this for myself at this point. 0W is the maximum expected score as an irreducible fraction. It's an uppercase T or an uppercase F. Right. Right, so what? Sequence of correct answers must be 50. Try like fixing one position. Consider we're computing the number of sequences that have exactly this value fixed. Maybe? It's still into the fourth is the problem. Or q to the fourth, whatever. Not n, q. I mean like 120 is the fourth. That's the problem. Do some weird n cube merging. That sounds so helpful. I don't know what they want here. That's the thing. Even then, it's still like into the fourth in memory. That's still a problem. I don't even have anything that's under into the fourth in memory. And into the fourth in memory will certainly not pass because it's 120 to the fourth times like 4 or something. Actually, no, times 16 because in 128. So you want something better. You want something nice like n to the cube, n to the cube, n to the 3. So we need to do that, ideally. Yeah, so basically we're taking this value, we're going on. Somehow it's escaping. Probably. to say. Should say something. Should say something. I don't have anything to say. We're gonna do better. Somehow fit this within n cubed. So let's what? Let's what? What do we let's? Actually, what do we let's? All the states are valid, I guess. It's like a constant optimization, that's not that helpful. So we really like a number of 8 different values. All of them are going to be the same. So specifically, like, there are really only 8 answers we need. So we can somehow compute the answer for a single location in n cubed, and we are done. But can we compute the answer for a single location in n cubed is the question. I don't really know if we can. Single location n cubed. Single location. Some combo we can do. So if we can write something. Maybe we can. We do some like sort of magic combinatorics. What am I saying? Wait, there are n choices. What am I saying? decently lightweight, like, combo thing. That's still really not that good. Suppose we compute, like, we can fill up the VP table for individual values in a really small amount of time. And for other things, might just to have faith that there aren't that many states. I don't believe that. And there shouldn't be that many states, but how does it work? Like, there are still a decent number of states. It's not that good. It's not that good at all. Could also do some weird prefix sums, but that's not that helpful. It's basically like 8n to the 4th. There's gotta be something else we can do, right? 8n to the 4th. Come on. It's not good complexity. It's, it'll pass, but it'll pass the first and second subtasks. But it's not good complexity. That's the problem. I need good complexity. So how do we get so good complexity? I'm not French. Like speaking like that sometimes. I'm just like wandering around for literally an hour. This is why I don't think it's that interesting to have face cam, but people seem to like it. So I guess that is something that will be done. Continue to be done. To the 97th. So we're basically interested in the number of answers and then also like the number of something. Yeah, like I said, it'll work in n-cube memory. Times 40 to the 4th is fine. Like, do they have some sort of guarantee on the largeness of the tests? Like the total size of the tests? No, usually they do, but this time they don't. So I'm assuming it's a wall of 120. solid amount of things. Oops, that's not hard to compute. It's like 864 into the fourth. That's even worse. Like, how many states do we really have? If we put some false down, it will add to everything. If we put some true down, it will also add to everything. 64 into the fourth. Jesus. It's not really 64 into the fourth. No, it's not. It's just 8 into the fourth. 8 into the fourth is like, it exists and it's awful complexity, but it exists. It's like it'll take over a second per test case or something. And that's not good. We gotta do better than that. But we'll work on the second test, I'm pretty sure. Like, 8 times 40 to the fourth is fine. Is it? Is that even fine? I don't even know. It's gonna have a pretty good constant, but not good enough to justify into the fourth. Number of values here. Take some value like that. Put it in. Give us an answer. And we'll eventually get an answer. Sync being huge is pretty nice. It's still like not that helpful. I can just like focus for some non-trivial amount of time, that'll be awesome too. I can not have like the mental fog that apparently really likes to come up, so that'd be cool. But I don't know. Maybe we can get away with like not the 8. Can we get away without the 8 somehow? It'd be feasible maybe? Like not really, but who knows? to be equal to the first thing and the other things also be affected. So, but at the same time, like, I don't know. What do we need? CN. SSJI. Let's see. SSJI is equal to T. No, the sum of counts is n. And do we know anything else? Like the number of... Oh, a lot of things happening. It's just stupidly large sample. Really don't know what to do here. Number of things. Number of things. Does my qualification hinge on this? People submitted this subtask. People resubmitted a lot. I have a feeling a lot of people are going to go down at some point. So it's probably still worth it to try and solve for full credit. Like, could at least, like, I don't know, submit. I really don't know what they want. Like, I could just, again, like 8n to the 8q to the 4th, 8m, whatever. is Q. Yeah, and in Q. 130, 120 to the fourth. I don't really know at this point. Probably don't want it to the fourth, but why did they make it 120? I don't know how CodeJam does things. It's the problem. I don't know what their tests are like. Are they gonna have a ton of small tests, or is every test gonna be huge? It's impossible to tell. So I guess I should prepare for every test being huge, but then like if it's not, then I'm totally screwed because I have a solution into the fourth, and if that's intended, then I don't even know what I'm supposed to do for that because it doesn't seem like it's gonna pass. And if it's not intended and it's supposed to be n cubed, then I guess I should think more. So I guess, yeah. It's basically like recalculating everything. I could just make sure this is right. I mean, it can't hurt to make a submission, I guess. Gonna write the basic DP and then maybe optimize it later if I can get an idea. Okay, so basically, we do use int 128s everywhere. I'll show you only that really. It's a good way to do this. Okay, undefined code. That's not nice. The hell is this? Does this work? Don't need that. Let's see. Let's see if this compiles. Just need one. Okay, I guess that works. Fine. Cool. Alright, so really what we need is we're going to 4 0 is an 8 I plus plus. Now if count I is greater than 0, let's see. So So if count I is greater than 0, then you can see I'm just totally tired for not that much of a reason. Minus count I. Do the DP for this and then continue. So should be that too. 4 j equals, right, actually, first we reset. In case the tests are nice, I'm not going to do memset. So now dp 0, 0, 0 is equal to 1. And dp. Alright, now for j0, j is less than count I, j plus plus. So we're going to do the push that many times. Not going to be so nice in terms of constant. So we set NDP to 0. Right? Yeah, NDP to 0. Now okay. So let's see. A plus I and 1. There's a method to this madness. Let me reverse the ordering of the loops. Wait, how do we do that? Alright, first this should be 8. Yeah, okay. So, NB is A, B, B, and this should be 2 and 2. Let me do the same thing here. C, B, C, C, C. And these would be 4, and once again 4. Now, if dpa b c is greater than 0, if there's even a point to doing this, yes, now we set this to that. Now we do count. For actually, how does this work? can get rid of that. And what that does is basically says barely, just barely. Okay. Can afford to recompute this. Memset C0 size of C. C0 0 is equal to 1. N equals 0. C and K is equal to C N minus 1. Okay. If K is greater than 0, yeah. Hmm. 158. Am I missing some brackets? Fine, unused, whatever. 1. Is this right? 120, choose 60. Looks good. Okay, so actually we can do better, like 15 and then 7 or something. Just to make sure it's exact. Yeah, we're good. Okay. So that handles that. We do binomial coefficients. Now we basically need to say well, j equals 0, j is less than or equal to count I, j plus plus. Actually, this should be, no, this should be k, k, because we need all these, count j. Do I need LL at all? I'm using M128 for everything, right? So I can basically just say, make these ints. No reason to do that whatsoever, but whatever. AV is equal to A plus K times NA plus count J minus K times NOA. BV is equal to A. Now B plus K times MB plus times NOB. So now we say make this a bit larger. Like shouldn't be necessary, but it shouldn't hurt either. Cubed times 16. Definitely enough memory, so we're good. Alright, so DP, AV, BV, CV, NDP plus equals C, N, K. No, not N. What is it? Let's count J, K times DP, A, B, C. Let's just print the expected values for now. Basically, now that we handle this, this should all be J. That's important. Well, actually, what I can do is copy these over first, because I will need them later. Then these should all be J. Should be J, 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 J. And this is going to be, so we get rid of all this. So like now, dp of, so how does this work? It's like A0 minus NA, A1 minus NB. How does this work? Oh yeah, NB, A2 minus NC. BB is equal to dp A0 minus no A, A1 minus no B, A2 minus no C. Res, actually this is just the denominator. So denominator is equal to VA plus VB, and in fact these should be in 128ths. Never overflow in my life, of course. And now we're going to say res of something. Res of I is equal to maximum of VA and BB. Now for, should we do the same thing here? Num plus equals res cur. CAI is equal to VA is less than VB, true. So CAI okay, no way this is ever gonna work first try. Probably not even compiles. Actually it does compile, which is surprising, but it's not gonna work first try. 3 over 1, 6 over 3, 24 over 8, 8 over 2. What? Alright, some of this makes sense, some of this doesn't. I guess that's a start. Oh, this should be, wait, no. You're only using dp values excluding n. Yeah, these are going to exclude n. We don't need to fill up to n. So, G is equal to, no. Into 128G equals GCD num den. GCD should work for that, right? That's useless. Num over G. I don't know what it's doing though. What is it doing? What does it think is happening? N is the number of characters. What? What is it doing? Oh, this should be cur. Maybe that's a thing. if I have the power to sit through and read this DP. It's like 1, 3. Okay, so 0, 0, 1. Seven, 1, 0. Oh, should not do that. This actually work. It's not this actually works. True, true, false. Oh, it's inverted. That's fine. True, true, false, true, false, true. Is that right? Let's get here. This is the moment of truth. This is what matters. It's getting that exact answer. What the hell? How the hell did this work? How did this work? What? How did this work? I'm so confused. How did this work? False, false, true, false, false, true. This worked. What the hell? Okay, well, I mean, I guess, yeah. Try it. Should pass, like, some stuff. Ideally. I mean, it worked for the massive case, so, like, how would it ever fail? The only place I can see it failing is maybe the construction of the string, but, like, at the same time, like, let's do this twice. Whatever. So again, the problem is it's definitely going to teal in the last section. Wrong answer. Okay. I'm very sure it's getting this right. Like, it got the massive case, so how did it fail anywhere else? But actually, does it get the massive case? I can't even see this. So it's like massive number 189, 154, 450, massive number over massive number. Yeah. FFFT, FTTT, FFFF, T, FT. It's literally the exact same thing. What? How useless must this huge case be? Okay. See if it works with multitests, I guess. Does that change things somehow? So I'll put this here, make this like 3 or something. What? What? How the hell does that work? Oh wait, it should be part of input too. Let me just close. Am I messing up now? Um, make it 1. Does it still fine? Okay, so it'll pass for 1. Then when I do multi-test, it has a problem. What is the problem? Fine, I'll just paste the test in. Jesus. Yeah, that alone takes 7 seconds. There's absolutely no way this will pass the final test set, but whatever. Still gets the same answer, right? Yeah, it gets the same answer every time. Same string. 120. Is it generating the right string? Like, say I do something non-stupid. So like 1, and then maybe like 5. Nope, not 5. 1, like 2, and then 10. So we can stare at this also. We're putting the case number, right? Like we passed the sample. Everything's up to 150. We're resetting between multi-tests, so we read in the values. We imagine it's going to be equal to 3 otherwise. Does that become a problem? It shouldn't, right? Like we're assuming it's fine. So set n equals m. We just like be normal and use normal variable names, but whatever. Okay. Set count 0, size of count. Sure. So we're doing that. So reset dp to 0, reset ndp to 0. So basically we're computing where this would be if we take this. So if this is false, yeah, and if it's true, then it's basically like XORing everything. K equals 0. One, 2. I equals max VA VB. So then this is VA is basically saying make this false. Alright, if this is less, if VB is better, wait, I don't understand this actually. What's happening here? So 001. So I have exactly one sequence where we make this false. It's like if the thing we're taking is like 1, for example, then not will be 1. So if it's true, oh, okay. Alright, that makes sense. That does make sense then. Now I don't know what's going on. What's happening? Like it works for this. TTFTFT. Right, so it's correct on the sample, it says that. Then it can be negative. Okay, can I code this in time? Alright, I guess we're gonna do the lame thing because I don't have a better solution to this. Don't know why this is wrong. So scene to end to M. For does this work? SSIJ minus O is equal to not. It's more like I shift J. Alright, this should be K. Yeah. Should be I shift K, I shift J, and 1. Now 4. Count I 0 is greater than count I 1. If we have more zeros than ones, then see out. A plus equals max 0 count. Alright, A and tote. Just comment out this whole thing. SSJ K minus O is equal to this. I shift K and 1. Okay, if pause, I shift J and 1. Yeah. Guess we're going for subtasks. Yay. Don't know what's up with that. Okay, so I mean we can try and debug this some more. If this fails, I don't know what's up. Maybe I just misread the problem or something. I don't understand how I could possibly pass the huge test and fail the tiny test. Like, what would happen there? What would cause that? So we're setting C. We're reading in SS. We're reading in count. Reading in N. Reading in M. Resetting count. Reading in CA. What is CA? Well, CA is being set. That's stupid. Doesn't really matter though. Plus plus. Minus count I. Plus plus count I. Is it really still not judging? choose K. Overflow is not the problem here. Is it wrong to... Alright, well, I don't know. So, hopefully that's a thing. Might just fail this. This is just not going to judge. It's just not going to judge. Okay. How have friends done? Yeah, people have solved it. Still don't understand. Like, why would this... What would I have missed here? Why would it fail on the first subtask? Okay, so we got that. It barely did anything. Alright, fine. That was disappointing, but still, I guess not many people solve this, so that's fine. Just don't understand. What happened? What happened? It'd been nice to be top 50, but I guess that's too ambitious. Nice. Or at least like get the second subtask. Get some effort for literally thinking this whole thing up. I'm gonna debug this. Is this wrong somehow? Maybe I should make these accurate. Nope. Still gets that right. Like, this is a local thing. There's no reason it would pass the sample and then... Maybe it was some inconsistencies with the way that worked. If that's the case, that sucks, but this shouldn't even make a difference. Wait, does it work for n equals 1? It doesn't, does it? What? I thought it... I guess I didn't test that. Should have. 1, 1. How does that work? Next, we can do that. Okay. I don't think it's gonna pass, but we can try it. Just being consistent with. I think it should only be one knot here, because it should be like the opposite. I just want to see the test. Might just look at the test if this fails, because I don't have the energy to debug this. Okay. Let's look at the test then. How's that make it? Oh, cubed. There's an O of Q solution? Huh. I guess that works. Yeah. I'm not done. Love you. Yeah. I just want to see the test. Do they now have the test here? They don't have the test, do they? One. Two. It works here. Does it work with this brute force? I mean, it's even the same sequence. What is it? What does this fail on? One, two, no, 2, 1. Is adding virtual students just somehow a bad thing? 5, 5. we have n equals 1, set that to 0, set this to 0. It's basically just creating a copy. And we assume n is 3, so it doesn't hurt otherwise. I mean, I'm using even the same like int28, int128 printing thing. Was that the problem? If I just use int128 with everything here, will this still pass? If m is greater than 10, exit 0. Just make it test faster. Like set everything to that. Pretty much. Maybe it's the M128s. That would be annoying, but can we try submitting again? So I made these all M128s. Should test quite fast. Still passes. Are they not? They're not going to release the test. They just won't have that. It's not going to have that. I mean, I want to fix this so I can explain it. Would be nice. What the problem here is? What even was the problem? I don't know what the problem is because I don't know. The denominator is like that. How does this work actually? Count j, choose k times the dp value. Again, this is all up to 10. We're going up to 10 here. It's not a problem. I really don't know. If I do something like all falses, it should. Suppose I don't do this. It should be 10 choose 5. Yeah. No matter what I do, it should be 10 choose 5. It's only one person. True or false for each question. The student scores the number of questions they answer correctly. answer all trues or something. Oh, I see. Yeah, we'll take the complement of that sequence. I'll give us 6. Not exactly one of those are correct, so we'll get a better expected value like that. We know expected value, we know linearity of expectation, we know all this sort of stuff. So the expected value of this, the maximum maximums. Maybe the whole idea is just wrong. I don't even know. In any case, I mean, something happened. So this resetting part? If I just reset these. Actually, wait, how does this work? What becomes what? Destination, okay. DP. Set DP 0 size of DP. Is that what the problem is here? Is that what you want me to do? I don't know how that makes a difference, but I guess that's what we're doing. No, wait, this should be NDP. I have no idea. Like I said, I'll try this. Will they eventually release the test? Who knows? Maybe they will. Maybe they won't. Actually, that might take a very long time. That's like 64 n cubed. Get TLE on the first test. Could happen. So we treat each question independently. Yep, that's what I've been doing. Yeah, that's what I did too. So all this is right so far. So we just brute force it. Yep. Like TLE. Could be what that means. It's interesting that we only have 4 questions though. Yeah, okay, I didn't realize compliments. Compliments are smart. That would have been nice. Get the TLE. Okay. I don't even care. I just wanna see what happens here. Make it 41 if I need to. Just make all these huge. It doesn't really matter. Alright, this will be my last try if I can't think of anything else. Oh wait, yeah, of course. Just made the thing smaller. How did it work then? FFT, FFT, FT, 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 41. Actually don't know why it would do that. Doesn't make that. I don't know. Actually, never mind. Try like one more time. See if the full resetting fixes it. Like it must have been multitest, because again, it passed this massive test. Does that totally fine? It's 40, right? Yeah. Does that completely fine? So basically all of my assumptions have been confirmed by the editorial so far. I mean, there must just be the DP that I miswrote or something. Guess that's how it'll work. Alright, well, I'll let that judge. I don't even know. Let's go over solutions. Okay. I guess that's how it is. That is unfortunate. Okay, yeah, so this would never pass the 3rd test set. Well, I have no idea what to do then. But what's the score for... Why did that fail? All I did was change... Like, why would it require it to go up to n? Because we're solving for n-1. Oh, we're not. Okay. That's why. Right. So if I did less than or equal to n, then it would have worked. Damn it. How many people have 75? That could be our score. Wow, Anton. Somewhere around this range. Like, would not have made any difference, basically. Alright, whatever. These problems are just a pain, honestly. Like, okay, so for this one, you have a list of integers. And you want to sort them. I'm going to list them from top to bottom. You want to sort them, but you can't like rearrange them. What you have to do is, the only thing you can do is you can pick some digit and stick it onto the end. So for example, I can pick a 6 and then stick that there. And I can pick the number 9 and then stick that onto there. And that would work. And then if I do it in such a way that this array is sorted, then it works. So for example, this and then this. We want to have it happen so that we use the minimum number of append operations. It's like the minimum number of, want to minimize the number of times we stick a digit on. So one way to do that is to note that it's strictly easier to like be larger than, like say we're trying to fix this element and we're trying to make it larger than whatever this is. Then like we might as well make this as small as possible, because we might as well have this be as small as possible, because then that will make it easier to do our operations down the line. And note that making it as small as possible is fine, because like every operation we do will increase the number. So doing operations to make it small will not hurt us. So really it's sort of like a bunch of like independent greedies where we're just solving for like basically we're looking at this number. We want to make it as small as possible while still making it larger than this number. Then once we do that, now we know what this number is, so we want to make it as small as possible while still working with this number, and etc. So I'm pretty sure the numbers can get huge. If I check the editorial, it requires strings, right? Numbers may become longer after each operation. Yeah, so this, yeah, like I was thinking, the integers could become huge. So really like what am I saying? My god, I'm so tired. I'm sorry, this is gonna be horrible. Yeah, so basically we have to work with strings here. We can't use integers or they will overflow. However, in this case it's fine to do so, because like every number is at most one longer than the previous. So basically this devolves into casework. So first, if this number is already greater than this, don't do anything, of course. Otherwise, we know that either the lengths, let this be A, let this be B. So the cases are, if B is already greater than A, then like the length of B is greater than the length of A. Or like simply like the length of B is equal to the length of A, and like the string B is lexicographically greater than the string A. Where lexicographically is like you compare character by character and find the first position where they differ. And then that's what determines the string. So if these are true, then do nothing. Nothing. Now we continue. So otherwise, either the length of B is still equal to the length of A, or it's not. Let's assume it is. So if B is equal to A, then the best thing we can do is stick on a 0, because we have to stick on something, and we might as well stick on the thing that will make it the smallest. So if length of b is equal to length of a, stick on a 0. Or if b is less than a, then once again we can actually still stick on a 0, because no matter what, the length will be smaller, or the length will be greater. Pretty sure this is right. I'm gonna check with my code to confirm, because I'm not exactly thinking the most straight right now. So yeah. So now we have to consider when the length of b is less than the length of a. So again, if we lexicographically compare, it won't worry about lengths. So if b is lexicographically greater than a, then basically the way this works is we have some b, and then we have some other a that's maybe longer. And we know that this blue part is greater than this orange part. So if we stick on some numbers within here, then automatically this number will be greater than this one, because this prefix is greater than this one. So really what we can do is, it doesn't matter what we stick on, so since we want to minimize it, we want to stick on a bunch of zeros. So stick on zeros until the lengths are the same. If b is less than a, we have the same situation, except now no matter what we do, this will be greater than this if these are the same length, because this prefix is already greater than this prefix. So we need the length to be longer, but when we do that, we're already guaranteed that it's bigger, so we can once again stick on zeros, but this time until length a is greater than length b, because we need to, or length b is greater than length a, because we need more digits. So if b is less than a, then we go until length of b is greater than length of a. And the final part is if this prefix is equal to this prefix. And this is the annoying part. So we want to try and keep a to be the same length as b. So really, the only way we can do that is to, this would actually be a lot more convenient in Python, but yeah, basically the only way we can do that is to say, we could have this. Now we need to, let me draw some more colors. Essentially, we need to compare these brown parts. We need the brown part in A to be larger than the brown part in B. But note that we have full control over this brown part in A, because this is the only predetermined part. We can stick numbers here to make this whatever we want. So we want to make this as small as possible while still making it larger than the brown part in B. So let this be like C. Let the brown part let the brown part in A be C, the thing that we're trying to make it greater than. So this is for notation, this is B and this is A. And again, this is B and this is A. Right. So essentially what we want is we want C plus 1. And in fact, that's it. We don't even have to do casework. We can just print the prefix of B and then plus C plus 1. The problem is we need the length, because suppose C is equal to 723 or something, right? Then C plus 1 is simple. It's 724. So it's the same length, but the problem is, what if C plus 1 is not the same length as C? And the only case where that happens is where C is some string of 9s. Then C plus 1 is equal to 10,000. Or C plus 1 is equal to a different length. It turns out that's the only special case. So you really only have to check for if it's all 9s, then increment that by 1. And otherwise you can simply do any sort of big num algorithm or something to increment the number by 1 and then print that. So code. Can I extend this? No? Okay, cool. Alright, so first case, well, like this code I have is basically the same, and you'll find the code in the description and stuff. So if length b is greater than length a, or the lengths are equal and b is greater than a, note that I corresponds to b and I minus 1 corresponds to a, the previous string. Then continue, because we don't have to do anything. Oh, and also, once you're done with these cases, then like whatever number you have for b, for example, this would be 700 here, then now we're figuring out what this number would do, and we need to make it larger than this one. In that case, it would be 1,000. While still making it as small as possible. So if the lengths are equal, we put a single 0 on as corresponding to here. Otherwise, the lengths are less. So if this is lexicographically greater, then we can use basic lexicographic comparison. Then like just make the lengths equal. Now we need to do actual like the definition of lexicographic comparison for the lesser case, because it's sort of more annoying, because b is less than a automatically, so no matter what, this will be true. So we need to distinguish the prefix being equal and the prefix being less, and you can like probably easier to check for equality actually, but whatever, I was not thinking straight this whole contest. So basically we find out if it's lexicographically less. If so, then we simply need to make it greater, and then put on zeros, and otherwise we check if it's all 9s. If it is, then actually, sorry, we don't want to make this 10,000 because we already know the length will be greater, so we might as well stick on a bunch of zeros again until length b is greater than length a. So it's actually the same code as this. We just need to stick on zeros until this has a strictly greater length. And otherwise, this is basically code for incrementing a number that's like huge. So you basically like, I can explain this logic. So basically you have some like prefix of 9. So say you have 323. It looks for the first thing from the right that isn't 9. So in this case, it would increment this to 4, and we're done. So we have like 239. Then this is a 9, so it would become a 0, and then we sort of have a carryover. So now we need to add +1 to the tens digit. So then we increment that, and that becomes 4. And if we have like 299, then this would become 0, this would become 0, and then this would carry over and become 3. So it looks for the first non-9 and turns all the rest of the 9s into zeros. Yeah, that's the idea. Cool. I really just gotta like play it safe with this. Honestly, I'm not playing it safe and it's screwing me over. Like, doing things that are redundant is fine. I could have just made this equal anyway, because I knew it was multi-tests. Alright, this one was kind of cool. Sort of. Maybe. Basically, the idea is you have a bunch of cards. All of them have primes on them. The fact that it's prime is important. And basically, you have a set of cards. You want to move some of them to the left side and some of them to the right side. Now, on the left, you're going to take the sum of all the cards, and on the right, you're going to take the product of all the cards. You want the sum to be equal to the product. Cool. Now, alright, so let's go over like a brute force solution or something. Suppose we fix the sum. Okay. Now, the reason the primes are useful is because of this handy dandy thing called the fundamental theorem of algebra, which I hope they do mention, which basically says that like it's fancy for just saying like every number can be decomposed into prime factors. So like, you know, for example, like take 37. Oh wow, that's prime. Take like I don't know, what can we use, like 24, right? So that's 2 to the third times 3, and etc. Every number can be decomposed into prime factors, right? So it's also unique. Like we have a unique representation of prime factors that have product p. So we need p equals s. And furthermore, we know which primes we need to get p, because we can take this unique prime decomposition. And normally prime factorizing numbers that are up to 10 to the 17th would not work. It just wouldn't work, especially if we're doing many of them. But the idea is that the primes there are at most 95 distinct primes. So we can prime factorize by simply going through all the primes we need and then dividing by them until we can't anymore. It's like basically we try to prime factorize it using only the primes we already have in front of us. And if we need more of a certain prime than we have, then like it's not going to work. And if we need a prime that we don't have, then it's not going to work. So basically we figure out the primes. So say like s equals, let's take some nice number like 60. So say the primes we have are 2 and 3. Sorry for this bracket. So the primes we have are 2 and 3. So 60, we're going to divide it by 2 until we can't anymore. So we get 15, which gives us 2 to the 2. And suppose we have like 1, 2, and like 3 3s or something, right? So we can decompose into 2 to the 2, but we don't have enough 2s. So right here, we automatically know this sum is not possible. But we might as well keep going for the purpose of the example. So now we figure out how many 3s it has. So now we know it's 5, and then here we get 3 to the 1. We do have enough 3s for that. And then here, we have nothing left to check in the set, so like this 5 is unaccounted for because it's not in our set. So the idea is we don't have to actually factorize the number. We're only trying the primes that are in our set and seeing if those are divisible. So then if this number is not 1, it's not possible. If any of these exponents are greater than the number of primes we have, it's not possible. Otherwise, this is possible. So the solution to the first two test sets would be simply to brute force the sum we have and then basically figure out the unique prime representation. Now suppose again we have s equals 60. Then this is 2 to the 2 times 3 to the 1 times 5 to the 1. Now assuming we have all of these in our initial set, these are what we're going to have to move over. So really, given that we have sum equals 60, the things on the left side are going to be everything but this stuff. And then the right side, we actually we already checked that. We checked if this product is possible. So because the representation is unique, we know the exact cards we're going to have to move to the right side, meaning everything else is going to be on the left side. So now we can make one final check if this sum on the left is equal to s. And if so, then we know that this is a valid sum. Since there are only 100 sums, it's around like, it's not that, actually no, there are more than 100 sums. It's, let's see, since there are a total 100 and it's up to 499, we have around like 50,000 sums. And it takes around not that much to check. So it's fine, it should be passable. Now, this is up to 10 to the 15th, which is much bigger. That's a lot more points. So, how do we do this? And the idea is we're going to use the same strategy, but we're going to optimize it a bit. We're going to be a bit smarter about what we do. And the way we'd be a bit smarter is we say, what are the sums we can actually have? Let's see. Let I be the sum we would get if we have everything on the left. So it's the sum. This is a terrible letter. I don't know. Let's just let like. I really don't know. A, sure, is the sum of the primes. So pi times ni. From I equals 1 to m. So it's basically just the sum we would get if we move everything on the left side. Right. So now the idea is like this product is going to be like, it's a product of numbers that are greater than 1. Every number is greater than 1. So like how many primes can we really take? Because the sum A is at most like, it's at most like 5 times 10 to the 17th or something, right? So like, how many primes can we really have? And it turns out that like 2 is the best number we can have to take as many as possible. So we're really interested in log of 5 times 10 to the 17th over log of 2, and it's 58. Huh, I just realized that. Interesting. My solution might actually fail at some point. I don't think it does, because this is like a gross upper bound, but should have been more careful. Whatever. Yeah, so basically the absolute worst we could ever have is like 2 to the 58. That's the worst product we can ever have. So as a gross upper bound, we can assume we'll only ever take at most 58 numbers. Right? So meaning the number of numbers we move from the left to the right is 58. Meaning that like, so what are our possible sums going to be? Well, because every number is at most 499, and we're moving at most 58 numbers. Again, this is an absolutely horrible upper bound. You can do so much better, because like every other prime is going to converge so much more quickly. Like 3 to the 40th is too much, for example. And like any number that's like huge, like 31, for example, that will converge incredibly quickly. So 58 is a very, very weak upper bound. But even so, supposing it is an upper bound, the numbers are at most 500. We have at most 58 numbers. So that means that the number of numbers we move from the left to the right, or rather the sum we lose from moving some stuff from the left to the right, is that even a letter? I don't know what I'm writing. The sum we lose from moving to the left to the right, sorry, cursive apparently, is 58 times 500, which is 29,000. Meaning that we can't be too far from A, because we're not going to subtract that much from it by moving stuff from the left to the right, and if we do, it's not going to be possible to make the product because it's too big. The sum that we would need would require too many primes, is the idea. So what we're basically saying is the valid range we need to check for S is between A minus 29,000 and A. So that's it. We do the same solution for the easy subtask, except now we only need to check these numbers. So this should run pretty fast. Good enough to pass at least. And again, 27,000 works. Probably like 10,000 or something works. I mean, it's really, 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 really weak upper bound. I cannot stress this enough. It's much less than 29,000. You could probably compute it directly, but I don't want to. So that's the idea behind this, that you only care about a few of the sums, which is kind of interesting. It's an interesting idea. That leaves this, and as you can see, I did not have fun with this. Alright, basically I don't know the best way to like do this, but I mean, I don't know, like, what am I trying to say? I don't know what I'm trying to say. Am I trying to say anything? I don't even know if I'm trying to say anything. What I know we can do is, what if I tried doing this again? Let me try submitting this, because like, why not, right? So I make these equal, make this equal, make this equal. I'm assuming it'll get TLE, but you know, it can't hurt to try. Maybe their tests are not as strong as I expect them to be, so they probably are though. They probably are. It's the most likely scenario, but in any case, it's like phone, what? Oh, right. 121, 128, 3, something bigger. Cool. Again, very much expect this to fail, but can't hurt to try, so why not? Can I make these up to n? Is this fine? Am I allowed to do that? Should be allowed to do that, right? There's no reason we would ever need to transition from... Yeah. Because if it's n, then it's like the maximum we could ever need. Okay. Right. I don't want to read this statement because it's like annoying. So I assume if you get this far, you know what the statement is, and if not, maybe you can consider reading it again if it's confusing or something. I don't know what I'm saying. The basic idea is what I did to get the first two subtasks is probably not the third one, but to get the first two, you can basically do dynamic programming, which basically says, this is the most naive version, that dp of I and A and B and C equals the number of sequences of length I with, like, so we have A characters equal to the first. Like, we have A characters of our sequence are equal to the first person's answers. B are equal to the second. And C are equal to the third. Very much assuming it will TLE. But yeah, it probably is, because it usually takes a very long time when it does that. So okay, now the idea is like to figure out a single point. Basically, we're solving for, like, say we have x and then like we have stuff to the left and to the right, and we're trying to figure out what this should be. Basically now we're trying to see if this is false, then like it's going to determine like the score we get from some of the other people. And if this is true, then it's like basically we're trying to figure out the number of sequences for everything except for this location, such that if this were false, it would satisfy the constraints. And if this were true, it would satisfy the constraints. And then we figure out the answer for false and for true, and essentially whichever one's larger, that's the character we want to make it. And then because linearity of expectation, stuff like that, where basically the expected value is like the sum of the total over the number of possibilities. So really we can just like treat it by, first we figure out the number of possibilities, which is like we can do this dp once for like all of n, and that would give us that, or we can like just do it however you want, really. Definitely TLE. Okay, that's sad. Fine. Yeah, I don't know. I do know how to do better now, but I'll basically just be reading off the editorial, so I will not have that yet. So the expected value is the total divided by the number of possibilities. And yeah, so we can figure out how much each position individually contributes to the total. And its contribution to the total is the number of is the maximum of the number of sequences where it's okay to make this false, and the number of sequences where it's okay to make this true. So basically, if this is false, then we automatically know like maybe person A gets a point. Then the number of points they need to receive from the previous, from like everything else, is whatever its score was minus 1. So like A0 minus 1. And if it's 0, then we know that all of this person's points have to come from these, meaning that we don't have the minus 1. It's just the number of points left is that. So we can do this dp. Yeah, basically we can do that. So that gives us an end of the fourth solution with end of the fourth memory, and the problem is memory, especially because like we need like a lot of memory, like int 128s for this, or long longs for this. Yeah, so that's not gonna work. But what we can notice is like there are not that many like possibilities, or there are not that many what am I trying to say? There are not that many like, I mean, look, we have 3 people, right? So the like for a single question, the answers, the set of answers we can get is like not that many. Like we could have false, false, and false. We could have false, false, and true. Or we could have false, true, and false, or etc. And we have 8 total. And then what I'm drawing. And then we would have 8 total. And also notice that like because we're solving these sort of independently, that all of these are sort of equivalent. And it turns out like this is something I didn't even realize, but like if we have false, false, and true, and then we also have true, false, and false, like these are complements of each other. So like basically these are equivalent. No, wait, no, not true, false, and false. Like true, true, and false. So really like if we figure out what's optimal to do for this, because notice that like no matter what we do when we're computing this, we're just like removing a position. And if we remove the same values, then it's equivalent. So really we only need to solve for like what if we remove a false, false, and true, or what if we remove a true, true, and false. And like whatever this is, it's just going to be like the values but swapped, because like this is the exact complement of this, meaning that whatever value is optimal here, say it's like x, then we can take whatever's the opposite of x, like not x, and then get the same result. So really we only have 4 things to compute. We have false, false, and false. We have false, false, and true. We have false, true, and false. And we have false, true, and true. And then some complements of those which we can sort of merge into that. And then when we reconstruct the answer, we just have to remember which one's complement and which one's not. What did I drop? How did I drop these? Okay. Alright, so this basically means that like we only have to run the DP 4 times. And we can do it in the n cubed way where the row isn't explicitly a part of the state. Like we can use the for example the space saving trick where we store the row mod 2 and then we only need 2 rows because we like only need the current one and then the previous one. So that will let you basically have, it's still O of n to the 4th time, but it's O of n cubed memory, which is fine. And so that will let you pass test set 1 and 2, as I've done. And then for test set 3, I can give like a very brief solution, basically like, or at least this is what the editorial says, it's pretty smart. Like because we only have 4 things, then like we can literally just brute force the number of combinations we have. And maybe use some combinatorics to figure out the number of ways to do that. Like if we have CI things here, and then we're gonna choose K of these to be false, and then like CI, we're going to choose K of these to be false, and then CI of them to be true, then it's simply just CI, or no, this should be CI minus K. Then it's simply CI choose K. Ways to choose K objects from CI to become false. And then we can immediately evaluate, like, using like bitmask stuff, like we can figure out how we can figure out exactly how many answers it matches for each person. So it's like a decently light O of 1, and it works pretty well. So I'm assuming like people might have passed with that just because it has a good enough constant. Yeah, because it's like it's at most like 120 over 4 to the 4th, which is like rather light, like 30 to the 4th. Yeah, that's very light actually. So even though there's like some not trivial computation, like not the lightest computation being done for each position, it's still not the worst, and so should probably pass within a reasonable amount of time. Anyway, that's how you do that. Or they also have some smart solution that involves like solving for a system of equations or something, but I'm not going to mess with that because I do not want to. How does this work? Yeah, there's some like stuff. Anyway, yeah, some smart thing. This will probably pass. Might implement it later just to like, just for display. But yeah, you can find my submissions here. The only problem with this code, this initial DP, is that I need to make all of these equal instead of not because of some oversight that I didn't realize existed. Namely that these could access up to exactly n even if the DP values in computation don't. So there's some sort of multi-test bug, which would like never show up except for apparently whatever test they had. So that's cool. Yeah, that's it. Anyway, this is awful. I'm sorry. This was like, I don't know. This just never felt good any of today. I still feel really tired. So I don't know how I'm gonna do in the round tomorrow. Cause that exists. Yeah. I don't know much more to say. Hopefully you enjoyed this contest, I guess. I really don't know what to say. Yeah. People did full self. Alright, whatever. I think that's everything. There are only 3 problems. Yeah, no. I'm repeating myself now. Goodbye.